Okay, so let's pick up from where we left this off yesterday. We were talking about the game of jump, where recall that we are given a grid of squares, and what you can do on your move is identify any square that's still available. And what that does is it has the effect of deleting from the board all the squares that are to the top of the chosen square, as well as to the right of it. So that's what's going to happen. And as is always, the person who is stuck and has no moves left is the person who loses the game. In particular, we're not allowed to remove the bottom left square. So if that's the only one that you're left with, then that's the point when you lose the game. So that's the game of jump. And here is the claim that we want to make about jump. If you're starting with a rectangular board, with more than one square, that's a reasonable assumption, because if you just have the one square, that's like starting nim with an empty heap, for example. So that's a loss for the player who starts the game, because you're giving that player a game that has no moves to begin with. So there's nothing to be said here. So if you have, on the other hand, more than one square, so I guess I should say somewhere that this is about jump. So I'm just going to say that it's a jump board. That's not official language, but it's just for us to remember what we mean. Okay, so how do we show something like this? We're going to invoke what is called a strategy stealing argument. And if it's the first time you're seeing something like this, it may strike you as a bit funny, almost as if we are cheating. But it turns out that it is a perfectly valid argument, just maybe feels funny. So what we're going to say is, well, suppose it's not an n. Then we have this n by m board. So there's some n and m, there's some dimension of board for which the game is in P. So I'll continue to call it a jump board. Right, so that's our assumption that we're making for the sake of contradiction, this assumption here. Right. So what this means is that no matter what move the first player makes, all the children here are n states. That's why we are currently a P. Right. Yeah, I think this is an idea that we're all comfortable with by now. You're an n if you have a P child, if you're P if all your children are n. That's one thing that I think is worth almost committing to memory, just because we're going to invoke it so often. So anyway, the point is that no matter what move the first player makes, they take the game to a position which is winning for whoever starts from that position. So in particular, and remember that this is a board that has more than one square, so it makes sense to talk about the top right square, and that's different from the bottom left square. So in particular, think about the specific move where the first player says, I'm going to eat up the top right square alone. It's just one square. It's not a very greedy move at all. It's actually the smallest amount of chocolate that you can chomp in one step is one only if you take up the top right square. So that's one of the moves that you can make. And at this point, you closely observe why this is a n, right? This is a n because must have had a p child. So the other player, your opponent, has a move that takes you to a p state. But whatever move that is, it has to be somewhere on the board. And let's say it's here. But notice now that this state here is actually accessible from the starting state. So you can actually choose to get rid of this also in the first step. And if you know that that state is winning for the other player, then that's a state that's reachable right from the beginning, right? So essentially, the reason this is called a strategy stealing argument is to say that, well, I'll be able to make a move in the first step, which is such that whatever move you make to win the game from here, after I've made my first move, is a move that I can actually replicate myself in the very first step. And whatever plans you have from here, whatever reason that this is P, that whole, remember, because these two are exactly the same state, this whole game tree is also available to us here. And so this is just a legit P child from the root. And if the root has a P child, it cannot be M, okay? And at least, I don't know about you, but the first time I saw an argument of this kind, I was like, well, that sounds like a very generic thing that can perhaps be applied to any game in any situation, and really does sound funny for that reason. But for example, if you try to show, let's see that if you try to show, for instance, that any instance of subtraction is in n using a similar argument, we know that there are instances of subtraction that are not in n. So let's go back to subtraction 1, 2, 3. What was this game? We said there are n tokens. You can remove on your turn, you can remove 1 token, 2 tokens, or 3 tokens. And what we know is that the P states here are precisely those where n is a multiple of 4, right? So if you try to strategy steal here, you're going to say, oh, let's see, suppose you have n and you want to show that you're starting with n tokens. And you want to make a claim like, oh, the first player always wins. Okay, now this is of course going to be a bogus argument because we know this is not true for several values of n. But let's attempt to strategy steal and see how we get stuck, which will hopefully point out some of the nuances in this sort of argument. So we want to say that, okay, in particular, suppose not, and suppose it was a P, then all its children are n, and from that end we have a P child, but we can pull in that P child to the top. So the key thing in strategy stealing is being able to find this pathway here, right? So you have to find an n child from n minus 1 who has a P child that's still accessible to you at the top, right? So what are the children here? The children from n are n minus 1, n minus 2, and n minus 3. And from here, if you go on to look at the grandchildren, for instance, we have n minus 1, n minus 2, n minus 3, n minus 4, n minus 3, n minus 4, n minus 5, minus 4, and minus 5, and then minus 6. These are the grandchildren. And notice that only some of these are accessible from n. right? So because you're only allowed to remove 3 tokens, all of these states are actually not accessible from N. So you may not actually be able to find a grandchild that is in P, which is also a child that is in P, right? And in fact, that's sort of what happens when you play at a 4 or an 8 or something like this. The winning pathway for the other player when it's a 4 or any multiple of 4 goes through in the second step to a state which is not accessible from the first one. So for strategy stealing, it's really important that you can find a grandchild that you can replicate that also happens to be a child. And this is, generally speaking, not going to be the case for most scenarios, but in Chomp, what is special is basically that if you look at the child, this specific child, which is really very conservative in what it chomps off, then all of its children, right, are such that, whatever is going on from here is also accessible at the top. So whichever of those happens to be in P is something that we can also pull in and take advantage of right at the top. Okay. So you really have to be careful about looking into your rule set and really being careful about ensuring that you can indeed actually pull out a P position from one of your grandchildren, which is also present as a child. But if you can do that, then that's a template of an argument to say that it must have been an N, because if the other player could win, basically in English, what this proof is saying is that if the other player has a winning strategy, then I can basically observe their strategy and mimic it right from the start. And so if they can win, then I can win too, but then that just doesn't add up. So it must be the case that I can win. So if you give me another player winning strategy, I can turn it into a winning strategy for myself. So that's the spirit of the argument. Okay, so that is strategy stealing. It works in some cases. Notice that it's non-constructive in the sense that I haven't actually given you a concrete pathway. So I haven't told you by this proof how you can win a game of Chump given a specific board. It's not a concrete strategy at all. But nonetheless, it's a proof that assures you that you have a winning strategy. So it's an example of what you would call a non-constructive proof. And you can think a little bit more about how you can actually devise winning strategies for Chump for yourself. Okay, so let me do a couple of more rule sets where, again, we won't be really getting into who wins or what the strategies are, but these are just fun games to be aware of, I guess. So here's a fun domino variant of NIM. It's called Dominim. Probably combining the words domino and NIM. So if you know what dominoes look like, they are basically these rectangular blocks, 2 by 1 rectangular blocks, and they have usually numbers on the top and bottom denoted by dots. And in Dominim, what you can do is you're given a collection of, instead of heaps of sticks or pebbles or whatever, you're given instead a collection of dominoes. And your playground is all the domino things on the top. All right, so a typical playground for Dominim is a bunch of dominoes lined up like that. And I don't know if that's too small to be visible, but okay. So your playground is all of the top halves of these dominoes. So what you can do is you can reduce the number of dots in any of these, right? And once you do that, you get to flip the domino, okay? And what is at the bottom comes on the top. So for instance, if you were to play here in this domino and there was only one dot on the top and maybe you got rid of it, then what that looks like after your move is made is this. The what was at the top goes to the bottom, and what was at the bottom comes to the top. You flip it around. And the next player may say something like, okay, I'm going to take out one of the dots from the first domino. And that would basically mean saying, okay, let me go back to what was there. There were 2 on the top and 3 at the bottom. So we're going to have the bottom come to the top. And what was at the top was 2, and you have to remove at least 1. And let's say you removed exactly 1. So that's going to be the new state. So this game progresses until all the tops basically become empty. And then at this point, you don't have any moves left. So that's an interesting NIM variation. I'll just leave you here with the rule set and not talk any further about strategies and so forth. But you can, it sounds like a fun game to play. It's a variation that I have not played at all. But go and check it out if you think it's interesting. There's another one called Fibonacci NIM, which will give us an excuse to learn about a cool fact about number representations. But let me write out the rule set first. So this is basically NIM. You can, again, have a collection of heaps, right? Now the first player in this case, so here are the additional restrictions. So the way this is put in the book is that the first player may not remove all the sticks. And I think this is just to talk about what happens in the first round. Because at some point, if the first player wants to win, they have to remove all the sticks. And they indeed do that in the example. So my best guess is that this is a restriction for the first round. But the more, I guess, non-trivial restriction is that no player may remove more than twice the number of stakes removed on the previous turn. Okay, so let's just maybe look at an example of how this might work out. Let's say you start with n equals 8 sticks. It's a single pile NIM here. And normally single pile NIMs are trivial because the first player can immediately empty the heap out. But in this case, that specifically is not allowed. So the first player has to remove at most 7 sticks from this particular pile. And for example, if they remove a large enough number of sticks, then the second player can remove the rest of it, right? So for instance, if I remove 3 sticks, I'm left with 5. And because I removed 3, the other player has the freedom to remove up to 6 sticks, which means that they can at this point empty the heap out. So removing 3 or more sticks is not a good idea for this reason, right? So what would you want to do instead? If you want to basically constrain the second player to not empty the heap out, you should remove 1 or 2 sticks. 3 or more is an immediate loss. What if you only remove 1 stick, for example, right? So then you come back to 7. And now the other player can remove 1 or 2 sticks at this point. Let's say that they choose to also remove 1. So they continue to constrain you to removing 1 or 2 sticks, right? So suppose this time you happen to remove 2. Again, notice that this is not a very bright idea at this point because removing 2 takes you to 4. But because you remove 2, you also upped the number of sticks that the second player can remove. So at this point, the second player can remove all the 4 sticks and finish the game in their favor. Okay. So that's not a good idea. You could have prolonged the game a little bit further by removing 1, and we could have checked out how that went. But let's come back to the top and say, okay, we got into a little bit of trouble by removing 1 stick, although we could have perhaps saved ourselves at the end. But let's see what happens if you remove 2 at the beginning. So then you go to 6, and this you don't immediately lose here because the second player is capped at removing 4 sticks. And this could go a few different ways. It could go to 5, 4, 3, or 2, depending on what the second player does. And if you have, well, I mean, here you have removed, so let me just write down how many sticks were removed. So this is when you remove 4, 3, 2, and 1. And in all of these instances, the first player now has enough of a budget to clear out the whole heap, right? So you can here remove all the 4 sticks because 2 times 2 is 4. Here, 3 times 2 is 6, and 4 times 2 is 8. So all of these are wins for the first player. But at 5, the first player can only remove 1 or 2 sticks. So from 5, the game sort of continues further. And let's say the first player, again, if they remove 2 sticks, they're immediately in trouble. Because if you remove 2, then you're left with 3. And the other player has a budget of 4. They can remove up to 4 sticks, so they can empty the heap out. So your only choice here, the only sensible choice, is to remove 1 stick, which leaves you with 4. And now, again, if the second player removes, they can remove 1 or 2 sticks. And again, they're immediately in trouble if they remove 2 for the same reason as before from the point of view of the first player. So they remove 1 again, so left with 3. And here notice that it's practically a no-go because you have to remove at least 1 stick. Again, even if you remove 1, you give the other player a budget of 2. At this point, they're going to win. Okay. So if the other player happened to make one of these moves where they remove 2, 3, or 4 sticks, right? Then they lose the game at that point. But if they choose to prolong the game by removing only 1, then they're going to eventually win, right? Okay, so we could ask ourselves, what are the P positions of this game? Who is winning, and so on. So to analyze this game, a useful tool is the so-called Zeckendorf representation of numbers. So let me spend a couple of minutes going over that. And if you run out of time, then maybe this will just be like a nice exercise to work with. What is the Zeckendorf representation? So when we write down any number in, whether it's in decimal or in binary or in your favorite base, we are essentially appealing to the fact that any number has a unique representation in terms of sums of powers of whatever that base is. So for instance, when we write down, say, 5 as, what do we write down 5 as? 4 plus 1. Or we write down 6 as 4 plus 2, and so on. These lead to the binary representations 101, for instance, or 110, and so on. And the fact that the binary representations are uniquely defined is basically another way of saying that any number can be written down as a unique sum of the powers of twos. Right? It turns out that apart from powers of your favorite number, so of course it's not limited to twos at all, you can pick your favorite number and you have a representation that's unique in terms of sums of powers of that number. And that would essentially be a representation of that number in that base, right? So the second row of representation basically says that any number has a unique representation as a sum of non-consecutive Fibonacci numbers. Okay, so let me write that down. And I'm assuming that Fibonacci is familiar. If not, then, well, just to make sure that the base cases are aligned, we're going to say that the first two digits are ones. So this is if n equals 0 or 1. So the 0th Fibonacci number and the first one are both ones. And from there on, you keep taking the sums of the previous two Fibonacci numbers, the previous two numbers in the sequence. So if you were to just expand out on that definition, f of 0 is 1, f of 1 is 1. What is f of 2? Well, you just plug it in here, right? So f of 2 is f of 1 plus f of 0. So it's 1 plus 1, 2. What is f of 3? Well, again, you plug it in here. So f of 3 is f of 2 plus f of 1, which is this plus this. So that's a 3. And it's really the same pattern. So you keep adding the last two numbers that you wrote down to get the next one. So you get 5, 8, 13, 21, and so on. So that's the Fibonacci series. And the claim is that every number can be written as unique. It can be written as a unique sum . So a unique sum, I'd love to say Fibonacci numbers, but we have to be careful. It's not unique if you're allowing all Fibonacci numbers. So in particular, for instance, any number can be written as 1 summed up n many times. But so for instance, 5 already can be written down as 1 plus 1 plus 1 plus 1. And it can also be written down as 2 plus 3 and so on. So if you don't impose this constraint, then we don't get uniqueness, right? But it turns out that once you impose this constraint of non-consecutiveness, then you actually get uniqueness. And let's maybe spend a minute just getting some intuition for why something like this might be true. So for any number, you can start off with a canonical representation using just Fibonacci numbers by saying, well, you can just write down n as, 1 plus 1. Let's just maybe do this for 7. So yes, it's just intuition by example. So this is, well, I mean, when I say non-consecutive, if you have the same number repeating, that's also a very special case of being consecutive. So this is not the sort of decomposition that I'm looking for. But now what I can do is combine two ones and make it a 2, right? And then I just pull in the rest of it. I notice that here I have like two consecutive Fibonacci numbers. It's like properly consecutive, one next to the other. And what I can do here is just replace this pair of consecutive Fibonacci numbers with their sum because I know that consecutive Fibonacci numbers add up to give me the next Fibonacci number. So this is the general idea. As long as you have two Fibonacci numbers next to each other, then that's a recipe for replacement, and you get rid of that local consecutiveness. But if you're still stuck, then you keep going until you basically stuck, and at that point you have what you want. And I completely agree. This is very very cool, very interesting. And in fact, the Zeckendorf decomposition leads to something called the Zeckendorf games, which is it's not exactly the Fibonacci nim, but it's in a sort of similar spirit. And maybe we'll have a chance to talk about that down the line. But for now, let me try to sort of just complete this exercise here. So we have this, and what's our current violation? Well, 1 + 1 would count as a violation. So we're going to replace that with a 2. And now 3 and 2 are again consecutive. So we are going to club those and turn that into a 5. And now our last violation remaining is a 1 + 1. And we turn that into a 5 + 2. And 5 and 2 are not consecutive. And this, okay, so I guess I've shown you one way of writing down a number as a sum of non-consecutive Fibonacci numbers. I'm not going to argue here that this representation is unique, so you'll have to take my word for that at the moment. But at least the recipe for getting to one representation, which only involves non-consecutive Fibonacci numbers, hopefully that's kind of clear. You have a starting representation, and you have a recipe for fixing things that are a violation of your constraint, right? So whenever you see in your representation two consecutive Fibonacci numbers, you sort of mash them together. I think I should make an exception for so basically the 1 and the 1 can be thought of as the 0th and the first Fibonacci number. Earlier, I did say that these repetitions can be thought of as an extreme case of consecutiveness, but notice that we're generally not going to, if you allow for a situation, for instance, where you have a 2 + 2, for instance, that's not going to combine to give you a Fibonacci number. So 4, for example, is not a Fibonacci number. So, so we do want to be careful about that. So if we have repeated Fibonacci numbers, we may not be able to fix it as easily. So really just think of the ones as being special, because although it says 1 + 1, those are really can be thought of as consecutive Fibonacci numbers because they're the first two Fibonacci numbers in the way that we have defined Fibonacci numbers, right? So, right. So I think, the next thing that I wanted to do is use this representation as a tool to talk about which positions are the P positions in Fibonacci nim. And well, it turns out that the P positions are the ones. So let me write this out, and maybe it's useful for some solo brainstorming or brainstorming with friends later in the day, and we'll come back and argue this when we meet next. But in Fibonacci nim, the only P positions are heaps whose size is a Fibonacci number. So think about, think about how when you have n sticks, you can write down n as a sum of non-consecutive Fibonacci numbers using the Zeckendorf representation, and see if that representation tells you how you can smartly remove the right number of sticks. Like I said, the gameplay here, there's some tension in. So on the one hand, you want to empty the heap quickly, but if you remove a lot of sticks, you give a lot of bandwidth to the other person also. And yes, Rito, in this case at least, the sum is it's a sum of these numbers, so we don't allow for negative signs. I believe that's also true when we are writing, when we are doing the base representation, which is the closest analogy that I could think of. So when we say that every number can be written uniquely as a sum of powers of twos, I think we really do mean positive sums, because I think once you allow for negatives, once you allow for subtraction, I'm not even sure that that's true anymore. It may not be unique, right? So for instance, 2 is written uniquely as 2 to the power 1, can also be written as 4 minus 2 if you allowed for subtraction. So I think the uniqueness to some extent relies on the fact that there are no subtractions. The analogy in the book is to the prime decomposition. So if you prefer that, it's just that the prime decomposition is a multiplication. So the powers of 2 or the powers of 10 or whatever felt like a closer analogy to me. But every number also has a unique representation as a product of primes. So that could be another way to think about the second order representation. So, right. So now I guess what have we? So, right. So in this game, I think the tension is about like you do want to remove stakes so that you can get to your empty piles as soon as possible. But if you remove too many, then you give a lot of bandwidth to the other player, who can then probably get rid of everything in one shot. So you don't want to remove too many either, but you probably also don't want to fall too short. So there's sort of an interesting tension there. And the Fibonacci sequence has a roughly doubling effect. I mean, the numbers kind of grow. In some sense, there's sort of an exponential flavor to the way that they grow. And the fact that your budgets are doubling, maybe there is some intuition for how you can use the non-consecutive Fibonacci sum representation to come up with a strategy whenever the heap size is not itself a Fibonacci number. So, and also maybe think about why are the Fibonacci sized heaps a win for the opponent. So I think I'm close to being on time. So I think this is probably like a natural stopping point. Anything else that I say will almost lead me to easily spilling over. So let me call it a wrap here at this point, and we will continue tomorrow.